Shall we start, sir?
Yeah, just one more. Shall I share the screen right away?
Yeah, sure. Yeah. I will do that. Yeah, he'll just make sure it's working. Sharing. Yeah, it's visible to us. Yeah. Okay. So we'll begin our final session of week-long celebrations of National Science Day here at MCNS. This is our final as well as the Science Day lecture by Professor Kembhavi. Initially, when we started planning, it was in the middle of the third wave of COVID, and we thought we will do everything purely online. But since the third wave went down very fast, now it has become a hybrid mode, like many of us are here in the auditorium, and we are streaming it in our auditorium, as well as since we had announced it online, we are also given the option for people to join through Microsoft Teams, as well as we are live streaming this on YouTube for if anybody want to watch it later or watch it live without interacting. So I'll straight welcome Professor Kembhavi to this program at MCNS. And Professor Kembhavi is a world-renowned astronomer, astrophysicist. He is currently Professor Emeritus at Inter-University Center for Astronomy and Astrophysics, IUCAA, Pune. Formerly, he was a Ramanna Fellow at IUCAA. Also, he was the director of IUCAA from 2009 onwards up to August 2015. He did his PhD at TAFR with Professor Jayan Narlikar and postdoctoral with Martin Rees at Cambridge. And later, he was one of the founder member of IUCAA when the professors from TAFR moved to start a new institute at IUCAA under the leadership of Professor Narlikar. Ajit also joined them, and he was one of the founder member faculties at IUCAA Pune. Professor Kembhavi works on galaxies, quasars, and other extragalactic objects, and various areas of high energy astrophysics, X-ray astronomy, radio pulsars, and application of artificial intelligence to astronomy as well as to biology. He has published large number of research papers and several books in English and Marathi. Kembhavi is involved in many national and international collaborations and is one of the key persons responsible for India joining the 30-meter telescope project, which Professor Anupama talked the other day in detail. So Professor Kembhavi, one of the key person in getting India into this TMT project, as well as the LIGO India project. He is now on the apex committees of this project and a member of LIGO USA Oversight Committee. In the field of data-driven science, Professor Kembhavi has led the Virtual Observatory India project for almost 15 years, which has made very important contributions to data management, analysis, visualization and development of tools for statistical analysis, etc. The project was carried out in close collaboration with the Persistent Systems, Anand Deshpande of Persistent Systems. You may be aware it's a well-known software company these days with a lot of contribution in the astronomy, astrophysics softwares, etc. He headed the big data project supported by the National Knowledge Network. Professor Kembhavi is also a principal investigator of the recently launched Pune Knowledge Cluster. This is funded by the PSA, Principal Scientific Advisor to Government of India, and brings together the academia, R&D institutes, industry in Pune to carry out capacity building programs and projects for the betterment of the city in the verticals of environment, health, electric mobility, big data, and artificial intelligence. Professor Kembhavi has been a member of Space Commission of Government of India, which is the apex body which controls the whole space activities, oversee ISRO, etc. He's also presently a member of ISRO's Apex Science Board. He was vice president of the International Astronomical Union and former president of Astronomical Society of India, chair of International Virtual Observatory Alliance, chair of Scientific Council of the Council of Indian Institute of Astrophysics. He is currently chair of Indian National Co-Data Committee. He's also fellow of Indian Academy of Sciences and National Academy of Sciences, India. Professor Kembhavi is also special to us because he was brought up in Hubli, Karnataka. So it's a close by town to us, people in Manipal. So with that, it's a warm welcome to Professor Kembhavi, and he'll be talking on the bending of light and the first black hole image. Over to you, Professor Kembhavi.
Thank you very much, Dr. Srijit, and for your kind introduction. I'm very happy to be here speaking to you about black holes on this Science Day. As all of you will know, on this day in 1928, Professor C.V. Raman discovered the effect which was later named after him. It's an extremely important effect with many, many applications outside of pure science. And in 1986, the government of India decided that this would be celebrated all over the country as Science Day. It's a very busy period in Pune, for example. This is my 5th meeting today on Science Day related things. I feel that these are fairly ridiculous way of giving a lecture where the speaker is very far away from the listeners. But then we have been living through a pandemic, and it's a very great good thing that technology has allowed us to carry out lecturing and other such academic activities in spite of the fact that we could not travel. I would have been delighted to go to Manipal for this talk. Even though I'm from Hubli, as was mentioned in my introduction, I'd never been to Manipal until a few years ago, about 4 or 5 years ago, when I went there for the first time. It's a marvelous place. I also went to Udupi, and I'm really looking forward to being there again. But now I'm going to talk to you today about the bending of light and the first black hole image. I mean, I started you see that the bending of light was first demonstrated by Professor Arthur Eddington during a total solar eclipse of 1919. So 2019, that 3 years ago, was the 100th anniversary of the eclipse, when the General Theory of Relativity became known to the general public, and Einstein became a scientist of the masses. So, there are many celebrations to commemorate that great event, and I started preparing a talk on it because I believe somebody must have asked me to do so. And then I got interested in light bending, and then I would like to connect up Eddington's work with not only black hole, the image of a black hole, which was first published in 2019, 3 years ago, but something which is even newer than that is how do you detect a isolated black hole? And a very nice reprint of it, which it is not yet a refereed published paper, but just a reprint which has been made available in the archives. A preprint, not reprint, but preprint which has been made available in the archives. And I would like to touch upon that very briefly too. So the first part of my talk, I'll be describing Eddington's work and the history, which is extremely interesting. And in the second part, I'll talk about black holes and the black hole image. So I'm happy to answer a few questions at the end of the talk. And I really hope that I'll be able to see many of you in person. So the historical part of my talk is based on a certain number of papers which are listed here, because I'm not very familiar with the thing. And then I read up some of these papers, and I learned quite a lot about it. So the total solar eclipse took place on May 29th, 1990. It was a long eclipse, 6 minutes and 50.75 seconds. I've seen only one total solar eclipse so far. There was one in Hubli many years ago, but at that time I was in England and I missed it. Uh, One in Hubli, many it could be. Hubli was one of the cities from which it was observable, and many astronomers had gone there at that time. Then I observed one from I had gone to Rajasthan to see one, which was like I believe 3 to 4 minutes, and it was quite spectacular. Now, now you see, this particular eclipse had a great role to play in science, as I'll describe to you now, and as I already mentioned. And the person who was behind it all was Arthur Eddington, who was the Plumbian Professor of Astronomy at the University of Cambridge, in what is known as observatories, and is now known as the Institute of Astronomy. So Eddington was a very great astronomer, and he worked on many fundamental uh, things connected with astronomy. In particular, worked on stellar structure and then the pressure of radiation in stars, subatomic sources of stellar energy, stellar diameters, what is known as a mass luminosity relation. He also worked on white dwarfs, though later he came in conflict about white dwarfs with Professor Subramanian Chandrasekhar, who was his student and whose work Eddington did not believe. Then diffuse matter in space, for forbidden lines, fundamental theory, and so on. So things like stellar structure, which even a non-astronomer knows a little bit about today, were not completely understood or absolutely not understood in Eddington's time before his work. In fact, at the start of the 20th century, it was not known to people whether stars are made of a liquid or of a gas. So the astrophysics was not there at all. And Eddington played a seminal role in our understanding of stars. So Eddington's contributions to general relativity. So he himself did some research on it, but maybe his contribution is to propagate knowledge about the theory. So Einstein worked on general relativity from 1905 to 1915. It's a long period of time. When he finished his special theory of relativity, he started working on general relativity. And then when he put out the final equations of the theory, that was in 1915, when the First World War was going on. Most unbelievably, we are right now facing a war. I mean, we cannot imagine such a war will start in the 21st century. But then on the other hand, for 2 years and more, we have passed through a pandemic. And no one believed that such a long and such a destructive pandemic is possible in this scientific world. So because of the war, there's no communication between Britain and Germany, who were the main adversaries in the war. And then, but papers, Einstein papers, were forwarded to Eddington by another great scientist known as William de Sitter, who was in Holland. And Holland happened to be a neutral country at the time. Eddington quickly understood the theory, digested it, and he became a great expositor. And then he realized that one of the prime predictions of the theory about the bending of light could be tested during a total solar eclipse. So Eddington used to work for several years on the subject and then wrote a book on it. And these are really marvelous books, The Internal Constitution of the Stars, for example, which discusses astrophysics very lucidly and very clearly. Then the mathematical theory of relativity, again, in describing Einstein's theory, for example. So here are some beautiful historic photographs. This is one Einstein and Eddington. I don't know where it is. It could very well be the Institute of Astronomy in Cambridge. And in another marvelous photograph, so you see these five great scientists here. As we have heard their names, so never imagined that they were a real person. For example, the person here in the lower right-hand corner is Lorentz. And I'm sure that all of you have heard about Lorentz transformations, for example. Right? So And it's only when you see a photograph like this do you realize that Lorentz was really not a mythical figure. There's a real person like you and I. This is Eddington, and here is Einstein. Here with the long beard is William de Sitter. And this, I believe, is Earthfest. I've actually forgotten. I should look that up. And then Eddington became very famous. It was not common for scientists to be famous at the time. And for example, he appeared on the cover of Time magazine. And so here is the hero of Eddington's expedition. This is Albert Einstein, and writing the equations of his theory. Right, so the general theory of relativity, which is the theory of gravitation, was given as a generalization of the special theory of relativity. And Einstein went through a series of very beautiful thoughts in arriving at this theory. And he finally, in 1915, he gave the field equations of gravitation, meaning the equations which govern the gravitational field. And, and then you see that this paper is just 3 pages long. That's because he had published a series of papers and he used to publish something and found it was incomplete, it was wrong, go to the next one. And the final paper was disarmingly brief, 3 pages. So what does the general theory of relativity, what is it? I mean, I could very nicely describe it to you, but given that may be difficult today, hope to do it sometime in the future. Okay, it's a theory of space-time structure. Meaning that in Newton's theory, we have the 3 dimensions of space, and then we have got time. And these are absolute. Meaning space is there, space is immutable, and time flows uniformly. It doesn't matter whether you are sitting on the surface of the Earth or whether you are far away from the Earth or whether you're sitting in a plane or a rocket, the flow of time will be the same. Meaning what? Let's suppose that you and I are here together in Manipal, and then we coincide our watches, and then you go away, you go very far, do whatever you like, and you come back after 10 years, and assuming that the watches are precise enough, Newton's theory says that the time shown by our 2 watches should be exactly the same. Now, in the special theory of, excuse me for one moment, please. Sorry. So, in the special theory of relativity, Einstein combined the 3 dimensions of space and time together into a single unified structure, which was called space-time. And then in his theory, there are a lot of weird things. For example, the speed of light is the same in all initial frame of reference. What it means is that if a beam of light travels at 300,000 kilometers per second, if you measure it in Manipal, and then somebody is sitting in a rocket which is going at a very high speed and measures the speed of light, then you'll get the same value for it. So, and then that leads to all kinds of very beautiful effects. And Einstein made the hypothesis that all physical theories must be consistent with his special theory of relativity. As it turned out, at that time there were only 2 interactions known. One was electromagnetic interaction, and the other was gravity. And it turned out that that electromagnetism, as described by Maxwell's equations, was completely compatible with Einstein's theory. It's a very beautiful result. Okay, then, but on the other hand, gravity was not compatible with it. So Einstein had to struggle for 10 years to get the correct theory of gravity. And then it turned out, most astonishingly, that the general theory of relativity was not only a theory of gravity, but also a theory of space-time structure. So what was Einstein's thing is that there are no privileged frame of reference like in the special theory of relativity. Like you could be sitting, standing, walking, running, accelerated, not accelerated. and still you must see the same physics. And then he said that the effect of the presence of matter, and when you say matter, then because of special theory of relativity, you also include energy in it. The effect of matter and energy is to curve space-time. And the particles, which particles move along special lines of this curved spacetime, which are known as geodesics. So what does all this mean? Is that the Earth is going around the sun. Newton would say, and that is because the sun has gravitational attraction on the Earth, and therefore the Earth goes around the sun. But in Einstein's theory, the Earth is simply moving along a geodesic. It is just that the curvature of space uh, puts it on a trajectory which appears to be going around the sun. And there is no force at all. So gravitation is not a force. It is the structure of space-time. It's a truly amazing theory. Then, but it is not as if Newton's theory is completely thrown away. General relativity is equivalent to Newton's theory for weak gravitational fields. Okay, which means that on anything that you could see on the Earth, either the effects of general relativity are quite invisible, meaning that it is as if Newton's theory is correct, or there are very small effects. And general theory of relativity comes into its own under extraordinary circumstances, like close to a black hole, for example. And those are the kind of things that we are going to be talking today in the second half of my talk. Right, and here are Einstein's equations. And Einstein's theory is considered to be one of the most beautiful creations of the human mind. And here in the top equation, which is the equation of the gravitational field of space-time structure, it is difficult for me to describe what it is, except to say that on the right-hand side is the presence of matter and energy, which curves space-time. At the left-hand side allows you, given what kind of matter and energy, to calculate what is the curvature. And the lower equation is what's called the geodesic equation, and which will tell you how either a material particle or a light ray would move in this curved spacetime. Right. So when you have a new theory, you must have new predictions. So Einstein made three predictions. One is the gravitational redshift. Second is the bending of light. And the third is the precession of the perihelion of Mercury. So I will quickly run through one and three, and then two will be the basis of my talk. So the gravitational redshift, as you see here in the diagram, means as light or a photon climbs up a gravitational field. So if I throw up a ball from the surface of the Earth upwards, then it gradually slows down because of the force of gravity and eventually comes back. Unless it is thrown with escape velocity, in which case it escapes to infinity. When I throw up a photon, then in Einstein's theory, it is also affected by the force of gravity. But the photon can't change its speed because it must have constant speed in all circumstances. And therefore, but what happens is that a photon loses its energy. And you know that the lower the energy of photon, the lower the frequency, the higher the wavelength, the redder the photon becomes. And therefore, a photon which is rising against gravity becomes redder, and a photon which is falling because of gravity toward the surface of the Earth becomes bluer. Now, this has all been tested and shown to be experimentally exactly as per Einstein's predictions. Then there's the perihelion of Mercury. So what happens is that if you look at the orbit of Mercury around the Sun, so then if there are no other planets present, and Sun and Mercury were the only two objects, then it would move along a perfectly elliptical orbit, as was predicted from observations by Kepler, established from observations by Kepler, and it is very easy to prove this using Newton's laws. Okay, then, but what happens is that Mercury, there are other planets in the solar system, and then the Sun is not perfectly spherical, and because of all those effects, it turns out that this ellipse is not perfect. and it moves in a form where it is as if the ellipse is swinging in space. And what is the result? Is that this point here, which is so close to the sun, which is the closest to the sun, so the perihelion, it keeps moving in space. It turns out that the total motion, observed motion of the planets, of observed perihelion, is 532 arc second per century. This is an incredibly tiny effect because 1 arc second is 1 upon 3600 of a degree. And this is just about 1/7 of that. And so the shift with beryllium is 1/7 of a degree per century. You can imagine how precise are astrometric measurements. Then it turned out that all various effects, which can be calculated using Newton's theory, can explain the whole of this except 43 arc seconds per century. And when Einstein computed the theory, to his great delight, he found that his theory exactly predicts this extra 43 arc seconds because of general relativistic effects. It was not required for him to introduce any new constant for it, just Newton's constant of gravitation. Then the bending of light. So Einstein's prediction is that, for example, if a ray of light passes close to the surface of the sun, then it must bend by an angle which is given by 4g m by r, where m is the mass of the sun and r is the distance, closest distance of the light ray from the center of the sun, which is for all practical purposes equal to the radius of the sun. And for a light ray which is grazing the sun, this is about 1.75 arc second. That's again a tiny effect, but it's perfectly measurable astronomically. So now, please understand what the effect is. Is that you have to see a light ray, and a light ray is bent with gravitation. But in order that there is a significant bending, we require a very massive body. And the most massive body known to us in our neighborhood is the sun. It has got a mass of 2 into 10 to the 33 grams. Now the problem is that if your light ray goes close to the sun, then you see then what will happen is that it will never be, this star will never be visible because of the bright light of the sun. So how do we manage it? That is the story which I'm going to tell you now. So, but I must also tell you that the bending of light also occurs in Newton's theory of gravitation. And in fact, it was known and it had been predicted. And then it turns out that that prediction is about exactly half of Einstein's prediction. So, what do we do? How do we look at a star which is behind the sun? And the idea is simply to do it during a total solar eclipse. So this is a magnificent picture of a total solar eclipse. So the face of the sun is exactly covered by the shadow of the earth. And what you're seeing around it is a corona, and here is a giant solar flare. But the rest of the sky will be black. So you'll be able to see a star here. So if a star is behind the sun, then it'll be difficult to bend it so much that it actually becomes visible here. But there are other stars around the sun and close to the sun, and they would all be displaced. And that is the effect which is measurable. So the total solar eclipse of May 29, it was quickly realized that the highest cluster, which is in the constellation known as Taurus, which many of you may have seen, which is close to the constellation known as Orion, and then that would be in the vicinity of the sun, and therefore it should be able to measure the stars in it. The person who realized that was Eddington, and then he recommended that the measurements must be made to his friend Frank Watson Dyson, who was the astronomer royal and the director of the Royal Greenwich Observatory, and whoever is director there becomes the astronomer royal. And then so he was also the chairman of the Permanent Eclipse Committee. So when he learned about this, he was very impressed, and he said that we must do it. Now, as you know, the First World War went on from 1914 to 1918. So So these people thought of this idea in 1970. They knew that an eclipse is going to happen in 1919. And then, therefore, and soon after the war. And so then they had to plan it all. And where was the eclipse going to take place? So you see that the eclipse occurred in this long blue band that you see here. This is the band of totality. And it started off in the middle of South America, and then it went on to Africa. So you could observe it rather than observe it from the middle of the ocean. You could observe it here from Brazil, or you could observe it there. And it was decided after some thought that you could do it from two places. In Brazil, there's a place called Sobral. It's a very beautiful place, and you can see this nice inset photograph here. And that was to be one place because the idea was to go to two places. And in case there are clouds in one place, for example, the other place would work out. And the second place was chosen on these islands, which are just off the African coast. Okay, so you see that there is this country called Gibbon, and just off Gibbon, and then these are islands of Sao Tome and Principe, very small islands, which are a country now. And so that is where it was decided that they would go to Sao Tome. You see how beautiful the place is. And people connected to the International Astronomical Union. Unfortunately, I was not one of them. Uh, went to Sao Tome in 2019 to commemorate Eddington's going there. Right, so Dyson, who arranged it all, the Eddington went to Sao Tome, but Dyson finally did not go. And then you see here that there's a clockmaker whose name was Cottingham. And you can see his shop. You see how beautiful the record keeping is. Actually, he was a watchmaker. It's very important to have accurate watches. And it is not known whether this person or this person is Cottingham. And then you see this small boy sitting here. And if he was still around today, then he would be one of the older persons on the earth at the present time. Right, so all these people went there. These people went to the old plantation building where this happened. And then the other person, this person with very long name, and he, Andrew Crommelin, so he led the expedition with other people to Sobral in Brazil. Right, so now when you observe the sun, you obviously can't turn the telescope directly at it. You need to use a mirror to cast an image of the sun which you can look at. So you don't need very large telescopes. So they had this 14-inch, 16-inch astrographic telescope, which means you could take photographs with it. And then as a backup, they had a 4-inch telescope. As it happened, this telescope didn't work properly, and therefore they had to depend upon data from the 4-inch telescope. And of course, there was an independent telescope in Sao Tome also. And here you see, you may recognize the Orion constitution. You can see half of it here. And here is Taurus with the star Aldebaran, which is very easily visible here, even from Pune, where I am. And then here you got the Hyades cluster. And then you are talking about stars in the Hyades cluster. So then what happened on the day of the eclipse? So all these people went there, they set up their equipment. On the day of the eclipse at Sao Tome, where Eddington was located, there were heavy clouds. But fortunately, the clouds thinned, and Eddington could obtain images for the last few exposures that he took. At Sobral, the weather was fine, but the astrographic lens did not work, and therefore the data from the backup 4-inch telescope was used. So you see how difficult life can be for astronomers. And here the plate, these are original plates, right? So plate number 281. And then you can see this particular star, which is observed on the photographic plate, it appeared here. Now, if it had not been shifted, then it would have appeared here. So you see that there's clearly a discernible shift. But you don't depend on only one star. So they looked at the shifts of several stars. They would have liked to have many more. And then as you move away from center of the sun, the shift will be small. And the various things, the problem is that as the focal length changes, then again there'll be a shift, or all those things have to be taken into account. And then here are the plots. So here is the radial displacement here, and on the x-axis, you have got the distance in arc minutes from the sun. So you see that as you move outwards, the distance decreases actually, and then you see as the distance is decreasing, the shift is increasing. And I told you that even within Newtonian theory, you can expect a shift. And then it turns out this dotted line would be the Newtonian effect. The heavy line would be general relativity, and this is the best fit. So you see that the observed points are completely consistent with general theory of relativity. So that was a great result. And it also became very famous outside the scientific circles. Right? So there are two great newspapers here, the Times of London and the New York Times. And then you see that as soon as the results were announced in November, so there came a revolution in science, new theory of the universe. And then, like all newspapers do, it says Newtonian ideas are overthrown, which is quite untrue. And then here it says Einstein theory triumphs. Right? So it became the general theory of relativity then became known to the general public, and Einstein became a very well-known figure. So this is a cover story of a magazine, and here you see Eddington, who also became very famous, and Sao Tome has brought in photographs with the image of Eddington on it. So this was all in 1919. The measurements were not perfect. Some people, in fact, constantly argued that they were not all right. So in the modern times, what happened was that the plate on which one of the plates on which the stars were located, so that plate was a copy of the Sobral plate. Okay, it was subjected to modern image processing techniques, image restoration, noise reduction, and removal of artifacts. And all this could be done because the plate is digitized, and then from there you could do all the modern image processing. And then in 1979, the results were obtained again independently. So with a 4-inch lens, they had got a result of 1.98 arc seconds as a reflection, and here the 1979 result is 1.90. So you can see a reduced error bar here. The the other lens had 0.93 because it was a problem, but even that result can be improved to 1.55 arc seconds. Then going ahead, getting completely new data, not only from solar eclipse, but lots of other techniques which look at the bending not only of light, but of electromagnetic radiation in general. So how do one express results? So you say that in general, for metric theories of gravitation, meaning that these are general theory is one example, but there are also other metric theories of gravitation. So there you say that the bending is given by this expression, half of 1 plus gamma, where gamma is a constant, 4 gm by r. So as it happens, in general relativity, gamma is equal to 1. So which should mean that delta theta becomes equal to 4 gm by r solar. Right? And then you recover Einstein's result. But other metric theories would have other value of gamma. So if you say gamma is equal to 1, then all the other theories would be ruled out. And you can see here in this diagram, just look at the top of the diagram. So this is the year of experiment. So and here is 1 plus gamma by 2. So if you look at 1920, 1990, 1920, then you see that Eddington's results are completely consistent with the value gamma is equal to 1, but the error bars are quite large. It could be between 0.95 or 0.93 and 1.1. But as you move forwards, then particularly here, VLBI, and this is very long baseline interferometry. This is a radio astronomy technique, and you see how narrow the error bars are. And then, so the modern value here, you see, so these values, that tells you that gamma is equal to 1 to within a factor of 10 to the minus 4. So that's the beauty of general relativity, is that as your techniques improve, then over the decades, and in fact over a century, everything that Einstein had comes from Einstein's predictions has proved to be completely correct. For example, Einstein's theory predicts that there should be gravitational waves which are observed, and gravity, after very heroic efforts, as you all know, they are finally observed in 2015 and announced in 2016, because the existence of gravitational waves. So now, when Einstein had looked at gravitational bending, he also worked out various effects called gravitational lensing, but he never believed that one would ever be able to observe them, because the techniques which we routinely use now uh, are completely common, were just absolutely unapproachable in the 1930s. So that here's the beautiful effect. So let us say that I got a massive star here, and exactly behind that star, in just one line with the observer, who's ourselves sitting at a telescope here, is a star. So this star, and this is what is called the background star, and this is the lensing star, and here I got the observer, and they're all in exactly a straight line. So like this ray of light is going this way, but like Einstein's prediction, it will bend here. But you see, because this is a straight line, there's perfect circular symmetry. So all the light which is lying along this circle should come here. So which would mean that uh, without the gravitational lensing, the rays will all go here. Only a small little bunch of rays will come here. But now the rows, all these rays will come to this point, which means that the object would look brighter than it is. And not only that, the image of the object would fall along this circle, which is known as an Einstein ring. So you see that here is the background object, here the lens, and the Earth is the observer, and then it should appear to be a bright ring here. Einstein never thought that this could ever be observed, right? And so you see what we have here in this beautiful image. The red part of the image is a Einstein ring which is observed by the Hubble Space Telescope at near infrared wavelengths. And then this green thing which you see here is just a portions of the ring which is observed by the Merlin telescope, and which is at 5 gigahertz, so which is at radio wavelengths. Okay, so what a beautiful thing this is. And here is another thing which happens that when you don't have such perfect symmetry, then it depends upon the relative positions of the background star and the lens and the observer. And here's the thing where there's a single quasar at the center, but you see five, apart from this image, which you see a ray of light coming to you straight, because of the gravitational lensing, you see four other images. And how do we know that these are not different images of the same quasar? Is because of a lot of observations have to be done to prove that. Right, and so lensing by clusters, a cluster of galaxy which leads to all this bending. Right? Then the last thing is gravitational microlens. So what you mean by that is you see the effect of one star on the other, because we have seen clusters and so forth, quasars, uh, by lensing by galaxies. This is lensing of one star by another star. And then you see here, as I told you, that as the star goes exactly behind the lens, the intensity increases because of the lensing effect. And you see this beautiful curve shows that. And then as the days pass, you see that it brightens as the background star gets exactly behind the lens. And as it becomes faint, there's a blip here. So you see the blip blows up. And what is this blip due to? It's a beautiful effect. There's a planet going around the star, and it is a planet which causes its own gravitational lensing, which is what you are seeing here. And you know that for hundreds of years, astronomers have tried to find planets behind stars, but planets around other stars, and they detected the first one in 1995, and this is the technique for detecting these planets. So now let us go to black holes. So one of the predictions of the first exact solution of Einstein's theory was given by Carl Schwarzschild in 1916, exactly 1 year after Einstein gave his theory. And then uh, Schwarzschild found an interesting effect became gradually understood better and better. So you see that Schwarzschild solution corresponds to a gravitational field around a point mass. So this is the kind of thing which is very easy in Newton's theory, and the force acting on the particle here would just be F is equal to g m by r square. And if r minus g m by r square, and if r were constant, the force would be constant along a sphere of radius r. Now in Einstein's theory also the thing is spherically symmetric, but there's an amazing thing happens. At a radius of 2 gm by c square, if you put the solar mass here, this is about 3 kilometers. At that radius, at that distance from this particle, there is something called the event horizon, which is not a real surface, just an abstract surface. This is known as the Schwarzschild radius. And the remarkable thing is that though light can escape from the inside to the outside, some of you know that such a thing can also happen in Newton's theory, where if the gravitating object is massive enough, even light cannot escape from the gravitational field of that object. There is no problem in Newton's theory because there is no limit to velocity there. If light cannot escape, another particle moving faster than light can escape. But in Einstein's theory, the speed of light is the maximum possible. Nothing can move faster than light. So if this object is so massive that light cannot escape from it, then we call it a black hole. So this is a black hole which is spherically symmetric. Then you can have a black hole. This is Schwarzschild. Then you can have other kind of black hole, you see, which are discovered as late as 1963. And this corresponds to a particle which is rotating. So you've got a point particle with a rotation. And then it turns out that this is an extraordinarily complicated solution, exact solution, and which was given by Roy Kerr. And it's called the Kerr black hole. Now the event horizon is again spherically symmetric, but then you have other structures which will not go into now. So what happens? What does the black hole do? So you see, if in Newton's in Einstein's theory, because we can say that light bends, you see that you've got a ray of light going here, as in the Eddington case, and when it passes close to the sun, it bends just a little bit, passes close to a black hole. Now a ray of light cannot move very close to the sun because the sun is an extended object. But if you have a perfect black hole, then a ray of light can move arbitrarily close to it. Now it turns out that the closer you go, as measured by what is known as the impact parameter, the closer you go, the more is the bending. Right? So that's completely natural because the gravitational field is stronger. The space-time curvature is greater. So every trajectory is going to be bent that much more when you come close to it. And then there's an amazing thing, is that at a specific radius, which is equal to 3 root 3 upon m times the radius, at that time, which is known as the photon radius, if a photon comes along specifically with this kind of impact parameter, then what happens is that it gets trapped on a perfectly spherical orbit. Right? So the photon goes, the gravitational field is very strong, so it just can't escape, but it doesn't fall inside either. Okay, and it just keeps going round and round and round. But if the photon is closer, then it plunges into the earth. And then, of course, if it is within the event horizon, then everything will be completely lost. So you see, Einstein's tiny effect predicted by Einstein for the sun, which was first measured by Eddington and his team. So you see that now we are talking of extreme effects because we believe that black holes are real. And when rays of light are in the vicinity of a black hole, they can be bent extremely. And what we are, and that is what has been used to produce the first image of a black hole. So for that, you use something which is known as an event horizon telescope, which, as we'll quickly see, is not a single telescope at all. but a network of 8 telescopes, right? And their idea was you use all these telescopes which are spread over a great distance, okay, so which can observe a black hole. Now, what kind of a black hole want they want to observe? It is what is known as a supermassive black hole. So supermassive black holes are found at the centers of galaxies. Like so, here is the active galaxy, which is known as M87, and you know it is active, meaning that there is something happening in it which produces far more energy than the stars themselves produce. And you know that it is active M87 because you see these giant radio jets. And as you increase your resolution, the radio jets, you can move closer and closer to the center. So it is understood, it is believed that at the center of M87 there is a black hole which is a mass of 6.2 billion times the mass of the sun. And the Schwarzschild radius of this in angular size, because this is at a great distance of 16.8 megaparsec. That means about 48 billion light years from us. Okay, the angular size will be extremely small. So the team, the Einstein, the Event Horizon Telescope team, found that either they could measure the black hole, supermassive black hole around M87, or the supermassive black hole which is the center of a galaxy. The problem is that the center of a galaxy is a very complex structure. There are a lot of effects there which should be difficult to analyze. And so the team decided that they will concentrate on M87. So what do you do to observe a black hole image? Is that first of all you have to use uh, VLBI, meaning very large, very long baseline interferometry, right? At a wavelength of 1.3 millimeters, which is called millimeter wavelength. It is because of various technical reasons that you need to go to the specific wavelength. And then you've got an event horizon telescope. So this telescope actually consists of several different telescopes. You see that there is one, there is America, there are various South America, and in Europe. And on the picture here, the detailed names are given. I don't have the time to go into that. But the idea is that because these telescopes are so far from each other, you use a technique, the path length of the light, the baseline is very long, so which means that you get a very high resolution. So when you when you use the high resolution, and then they form an image. Please understand that this image that you see is not an optical image. It is a it is millimeter observations which have been rendered as an image so that our eye can see it. And this is the famous picture which many of you have seen. And then you appear to see this disk here. And then at the center there appears to be just a black thing there. So it took me some time to understand this image actually. Let me try to quickly describe it to you. Is that let me first show you another image so that you know what it is not. So this is a galaxy which is known as MGC 4261, and it is also it is 3C270. It's also a radio source, and you see all these things going around. At the center of it has been observed by the Hubble Space Telescope. And what you see here is very similar to an image that I just showed you. But this is something completely different. So what happens is that here at the center, you see a bright source, which is the source around the supermassive black hole, but it is actually a luminous source. And what you see here, the black thing, is a disk of dust which is going around the center. Right? So now the black hole image, which looks like that, is not a disk which is going around the center, a disk of dust. What is happening here, to understand this image, just imagine that the sky were illuminated uniformly and then there was a black hole sitting there. And so what would you see? You may see the light which is coming from around the black hole, but but then when those beams of light move close to the event horizon of the black hole, they will not be able to reach us because they're all absorbed. So at the center, you will see a shadow. So when the Earth goes across the face of the sun, you see a shadow of the Earth there, right? So similarly, here you are seeing a shadow of the black hole, whereas the black hole itself is not luminous, but you mean the shadow in the surrounding light has been observed for it. So this which you see is the black hole. And what is happening here, this is not a disk which is going around the black hole. There are various ways of interpreting it, but one simple way is that there is gas around the black hole which is falling into the black hole. So you've got a spherical surface there. And then you are not seeing a light which is coming from the vicinity of the black hole. And what is this bright half ring that you see here? So that is because this spherical structure is actually rotating around us. And it is rotating in such a way that the part of the bottom is coming towards us, the part of the door is going towards it. And why is that? And because of relativistic effects, the part which is coming towards us gets brightened, and the part which is moving away from us becomes dim. And then this black hole is not perfectly black, and that is because the light, because you see that this is not, it is not the background light that you are seeing, but it is light which is emitted by gas which is falling onto the black hole. This is, of course, a very simple interpretation that I'm giving you, but this is completely consistent with observations. And then you see here one very interesting thing is that these observations were made in 2017 and were published in 2019. But 20 years before that, uh, a, a team of three astronomers had carried out simulations using GRMHT. What is GRMHT? It is General Relativistic Magnetohydrodynamic Models. So these are extraordinarily complex numerical calculations. And we show you how a plasma, which consists of charged particles, moves in a hydrodynamic situation, in a magnetic field. And because it's a fluid, you have to use hydrodynamic. And because it is close to a black hole, you have to use general relativity. So using that, you see that these predictions have been made. And then when these are observed by radio telescope, this is what you expect to see. Okay? And then you see that these images are so extraordinarily close to the image that I showed you a moment ago. So this is a very beautiful confirmation of very difficult modeling and by very difficult observations. So it's a great triumph. And now the same team is now looking at the black hole at the center of our own galaxy. These are very painstaking observations. So I will end my talk. I come to the end of my time. I'll end my talk by showing you this very recent result, 2022. So you see, if a black hole is at the center of a galaxy, the supermassive black hole, I showed you how it can be observed. But imagine that there is a black hole which is moving, which is isolated, and which is a stellar mass black hole, 4, 5, 6 times the mass of the sun. And how do you observe it? Because it's a lone black hole. See, if the black hole is a binary system, then you see what is known as an X-ray binary. Because the black hole sucks in matter from the binary companion, heats it up, and that emits X-rays. And those are known. We know about 100 X-ray binaries in our galaxy. Okay, about half of which are black hole binaries. But if you're isolated black hole, you can't see it at all. But again, you can use microlensing. So just imagine that there's a star sitting here, and a black hole is moving. And then you see as the black hole moves past the star, you see gravitational lensing. I've already described that to you. And then what would happen to the light coming from the star? So it would have a certain intensity when the black hole is far away. When the black hole comes, it is lens, so it's more intense and then it goes down. Exactly like the way that you discovered the planet. I showed you the observation. Right? Except that because it's a black hole, the details are different. And then you see that on the top, there are theoretic predictions. Two things will happen. One is the change in brightness because of lensing. Secondly, just as in Eddington's expedition, the position of the star changed because of the thing. Here, the position of the star that you're observing, the background star will also change. And this is a change that is predicted. Okay, so so you see, we have the theoretical calculations, and Kailash Sahu, who is a senior astronomer at the Hubble Space Telescope, okay, and he and his team made these measurements of this particular star, and they measured it from the ground to get see how intensity varies because this has to be done over a long period of time. And they made measurements using the Hubble Space Telescope to see how the predictions are changing. And you see that in both cases, the dots are the observations, and the smooth line which is drawn through them is actually the model. So the models fit the observations very well, and you can conclude from the model that the mass of the lensing black hole, the mass of the lensing object, you don't know that it's a black hole, is 7.1 times the mass of the sun. It's at a distance of 1.58 kiloparsec. That just multiply this by 3, about 4.5, 4.6 thousand uh, light years away. So you see, then how do you know it's a black hole? That is because, first of all, you can't see the object, so it is not a normal star. Then in that case, if you can't see the object, it could be a collapsed object, which could either be a neutron star or a black hole. But the fact that its mass is 7.1, meaning more than 2.4 solar masses, means that it cannot be a neutron star, it must be a black hole. So this is an extremely good candidate, and more measurements have to be made uh, for using the bending of light to detect isolated black holes. Right, so I stop there. Thank you very much.
Thank you, Professor Kembhavi, for a wonderful talk. Hope you can take few questions from the audience.
Yes, please.
Yeah, so it's open for questions. Anyone here in the auditorium?
I have a simple question. I am not knowledgeable about it. In the
Yeah.
geodesic measurement that you are taking, because it is in the geodesic that you are measuring the of gravitational field. Is the time dilation effect taken into account for finding the distance in kilopascal per second?
See, what happens is that in order to find the distance, you really don't need time dilation or anything like that. Okay. But for example, when you're producing the image or when you're doing the gravitational lensing, these are very these are very carefully done calculations. So the bending of light is there, the time dilation is there, and how they come. So it has, what you do is that you take the geodesics in Einstein's equations, and then you solve for the geodesic equations. You cannot solve them analytically, you solve them numerically, but by building in all the effects in it. So these are very detailed calculations.
Yeah.
In the gravitational lensing events you showed, so is there any the distance between the 4 images what you have shown for one object? So in such calculation, is there any minimal distance up to which it can move and then it will go away? I mean, is there something like that, or is there any?
Are you talking about this one?
Not exactly this one. It just came in mind from one of your slide where you have shown that one star was imaged in the in the 4 stars due to the.
Yeah. Oh, so that was one quasar imaged as 4 quasars. Those quasars are very far away. They are not within our galaxy. They are at cosmological distances.
No, my question was, is there any possibility that the 4 images of the same quasar will come together due to the proximity of that lens object or the object which is being lensed?
Yeah.
So is there any possibility like that, or I mean, is there any minimal distance between these 4 images, or 4 or 3, whatever the number of images?
Yeah. Okay, so it is like this. What you see is a very sensitive function of the lensing geometry. Okay, it depends upon how far is the quasar and how from the lensing galaxy. This is not lensing by a star, it's lensing by a whole galaxy. Okay, and so it depends upon how it is located relative to the center of the galaxy and many different things. So what you can do is that you can do exact calculations of what you expect to see. And then this particular thing is a very fortuitous observation, because the quasar and the galaxy are so located relative to the observer that you see these 4 images. Sometimes you see 4 images, sometimes you see 2 images, sometimes you see the images which are not separated at all. Then you will not be able to make out that there are 4 images. Whereas if the quasar were exactly behind the center of the galaxy, then you might even see something like a ring. Okay, so it all depends on the details.
Hello, sir. This is Krishna. Very nice talk. I want to know how much the role of the structure of the magnetic field as in contribution to the image of the black hole.
Yeah, you see, it is not the structure of the magnetic field itself. What happens is that it is not really the image of the black hole is a completely general relativistic effect. The magnetic field is important in order to decide how the matter is distributed. Right. So actually, some of the calculations are done assuming that the matter is in a spherical structure around the black hole, but in reality, it is not a spherical structure. It is a jet which is moving. Okay, and the details of the jet are magnetohydrodynamic, because the jet consists of a plasma which is moving in a magnetic field, and that is why you need to do MHD calculations.
Okay, thank you.
Hello, sir. I'm a BTech student, so I was wondering how, like, if primordial black holes are ever observed, and like, how do they like measure the mass of a black hole? So that I was wondering, like, how.
You see, what happens is that you have to know the context. So if you have a mass, if you've got a supermassive black hole in the center, the mass of the black hole in the center of a galaxy was extremely elegantly measured. You know what Kepler did? So Kepler looked at the data on Mars, and he established that Mars is going around in an ellipse around and then the sun is sitting at one focus of the ellipse. It took him 20 years to do that, but he did it. And he did not know the theory behind it. It was pure observation. And then once Newton gave his theory, not only gave his theory of gravitation, but also developed the calculus which are necessary to do the calculations. And then it was possible to prove that the orbit of Mars must actually be an ellipse with the sun at the center. And then you could use Newton's law of gravitation to measure the mass of the sun. So the mass of the black hole at the center of a galaxy has been measured exactly in that way by considering the motion of stars in the vicinity of the black hole. It's a remarkable measurement, and for which the Nobel Prize has been given to Gales and Guess. Then, if you've got a black hole which is isolated, then it is much more difficult. And so now you saw that I told you that the mass of this black hole is expected to be 7.1 solar mass. How do you do that? You do that by fitting the observed data to the lensing, to the what is expected from lensing, and that is a sensitive function of the mass. So that tells you that is you're inferring the mass of the black hole. So you have to use different techniques depending upon the context.
Hello, sir. Thank you, sir, for this wonderful talk. I had a question regarding the image of the black hole. You had told that the light which we are seeing is because of the gas which is emitting, the gas which is surrounding the black holes which is emitting.
Yeah.
Then if it is surrounding, if it is rotating, then the gas which is below it is getting beamed towards us, and gas which is above, which is beamed away from us. But
Yes.
then why aren't we seeing which is on the surface region? Like if it is rotating, then on the surface also there will be gas which would be emitting. So we should get the emission.
You are. You see, it is like this. I told you that these measurements these are millimeter measurements. Okay. See, what happens is that when you do, you are measuring at millimeter wavelength because the plasma is transparent to the radiation at that wavelength. Okay, and when the plasma is transparent, then you are adding the radiation which is emitted along every line of sight. So when you're looking at the sun is opaque. Okay, so therefore, because the gas density is high in the sun and it's completely opaque. So what does it mean? Is that you are not seeing the radiation which is emitted from the center of the sun. You're only looking at the radiation which comes from the top 50 kilometers of the sun. So the sun has got a radius of how much is it? 700,000 kilometers. And you are seeing light which is coming only from the top 50 kilometers. In the case of the black hole image, the gas is transparent. So you are seeing gas coming from all over, and the image that you see takes that into account.
Good evening, sir.
Yes.
Very good lecture, and we could understand to some extent about
Thank
the
you.
black holes. These black holes could be studied only with radio astronomy, or even certain optical measurements can also be done. Like, for instance, now we are going in for that NLST program and also Aditya and all that. Can we also use these instruments to look at the bending of light from stars and things like that?
Aditya, you're observing the solar corona, basically. Right? And you're looking at the sun in all its glory. You'll not be able to see anything in the background. The telescope always keeps pointing at the sun. That is the beauty of it. But you see that as I told you, you can look at black holes with the optical, you can look at the radio, you can look at them with the X-rays, and there's many measurements which do this. So here it is all contextual, meaning what are you trying to do? So here you are trying to construct the image of a black hole. So it turned out that using millimeter wave radiation is the most convenient way of doing it. But there will also be other effects. Black holes can be observed. You're not observing the black hole, you're observing the plasma around the black hole. And that can be done at very different wavelengths. I have a question. Are all the people asking questions actually physically sitting in a hall, or some of you are also away from Manipal?
No, all these questions asked till now are in our auditorium only.
Yes.
Yeah. So.
And that is why they are able to do that voice instead of typing it in.
Yeah. There are few people still on Teams as well. If they have any questions, they can unmute and ask the question. Yes. Right now, yeah. Actually, now initially we thought everybody will be online, but now since Corona came down, we decided
that's right.
People can come to the auditorium. Be better.
Yeah, you see, the thing is that when the thing is down, when Corona is down, then you just meet whenever you can, go wherever you can. You don't know what's going to happen in 2 months' time.
Yeah. That's true.
You don't know what's going to happen in 2 days' time because of the war.
Yeah. Okay. Is there any? Okay, it's enough. One more question.
Thank you for the interesting talk, sir. It's remarkable how the astronomers now have the shadow of black hole, the image. If there is any advancement or improvement required on the observational front so that we could have better constraints or a more better image.
Yeah, obviously. So this is the first ever image which has been released, and this was measurement done in 2017. After that, many other measurements are being made, and this is just the infancy. It's going to get better and better and better.
Okay. If there are no more questions, I will request our academic coordinator, Professor Gopal Krishnan, to for a vote of thanks.
Thanks, Professor Ajit Kembhavi, for that illuminating talk. MCNS is grateful to you for finding time by bending your tight schedules to throw some light on the invisibles, namely the black holes. I have heard a slokam in Sanskrit which says, Natad bhasayate surjaha na shashanko na pavakaha yad gatva na nivartante tad dhama paramam mama. It refers to that. It says that. It doesn't say which that is. It refers to that which cannot be lit by any power source. It is something which cannot be lit by any power source, like sun, moon, or Agni, fire, or anything. Anything that goes there never returns. This is exactly what the slokam says. Yad gartva, whichever goes there, na nivartante, means never comes back. So the description almost is of a black hole. Nothing escapes from it. To study an object, especially an astronomical object, you need a light from there. So there is also one, I don't know the actual quotation, but I have heard it. If you want to observe or study a star, you capture a ray from the star and go along with it. It's a statement. I don't remember what it is. So you need a light from there or a clue from there. Regarding the black holes, we don't get a light from there, but we get clues. For the present day investigators like Professor Kembhavi, even black holes give clues. Once a black hole gives a clue, it has no escape from these scientists. What a wonderful talk it was today. MCNS is immensely thankful to you, Sir Dr. Ajit Kembhavi, for today's talk and also for being an advisor for us. We will have many more occasions to listen to you. Thanks again.
Thank you very much. I look forward to meeting you all someday.